Welcome to The Explainer. If you're the kind of person who loves breaking down complex ideas into really clear, structured insights, well, you are in the exact right place. Today, we're going on a pretty epic visual journey. We're going to take something incredibly familiar, a concept you probably learned way back in middle school geometry, and scale it all the way up to the size of the entire planet. Honestly, get ready to completely change the way you look at a globe. So, here's the big question to kick us off. What on earth does a 2,500-year-old math formula have to do with a three-dimensional map of Seoul, South Korea? It sounds like a massive stretch, right? But I promise you, by the end of this explainer, we're going to do this huge visual zoom out that perfectly connects totally abstract flat mathematics to the actual physical spherical geography of the Earth. Part 1. Pythagoras' hidden secret. To get to that big reveal, we need to start with something familiar, just to build up our confidence before we drop the real mind-bending twist. Okay, let's dive into this. Take a look at that top diagram showing the red and blue circles attached to the sides of the triangle. Let's just totally ignore the complex algebra for a second. We all know Pythagoras' theorem, right? A squared plus b squared equals c squared. Usually, it just tells us about the lengths of the straight lines in a right-angled triangle. But what we're looking at here brilliantly shows that this formula isn't just about straight lines at all. It actually hides this beautiful secret about round shapes, too. Let's walk through the logic step by step. First, we start with the three straight lines of a right triangle. Then, imagine taking each of those lines and using them as a literal diameter to draw three perfectly round circles. What happens? You get two smaller circles from the short sides and one big circle from the long side, the hypotenuse. And here is where the magic happens. If you calculate the surface area of those two smaller circles and add them together, they perfectly, exactly match the surface area of the big circle. Part 2. Expanding from lines to areas. Okay, we've basically just leveled up. We are transitioning our thinking from basic, one-dimensional straight lines into the two-dimensional concept of surface areas. This breaks it down super clearly. In that first row, we've got our 1D lines, standard Pythagoras, nothing crazy. But look at the second row. When you use the triangle sides as diameters, the radii become a over 2 and b over 2. And if you plug those into your standard area of a circle formula, pi times radius squared, the fundamental law of Pythagoras still holds perfectly true. The sum of the two smaller areas equals the largest area. It's essentially an unbroken rule of area conservation. So, the absolute crucial point to take away is exactly this. The area of the two smaller circles perfectly matches the big one. I really want to cement this beautiful, flat, 2D geometric truth in your mind because it's literally the engine that's going to drive the rest of our exploration today. But wait, how do we actually take flat geometry and wrap it around a sphere? Well, we need a bridge, and that bridge is Thales' theorem. It basically states that if you draw a line straight across the center of a circle, so the diameter, and then connect the ends of that line to absolutely any point on the edge of the semicircle, the angle you create will always, without fail, be a perfect 90-degree right angle. This means you can slide that point anywhere along the curve, and your right triangle stays perfectly intact. Part 3. Zooming out to 3D Earth. We have our 2D rules, and we've got our bridge. It's time to shift our scale. Let's zoom out from a flat piece of paper and apply this whole thing to a spinning three-dimensional globe. And this brilliantly illustrates our massive scale shift. Now, we're mapping our math directly onto the Earth itself. The starting point here is Seoul. Now, I want you to imagine drilling a hole straight through the center of the Earth to come out on the exact opposite side. That opposite point, that's called the antipode. The straight line connecting Seoul to its antipode, going right through the Earth's core, is literally the diameter of the Earth. Let's quickly contrast what we've learned so far. In flat 2D geometry, we just had this hypotenuse we called c. But in our 3D spherical geometry, the Earth's physical diameter, represented here as 2r, literally becomes the ultimate hypotenuse for our triangle. Think about that. The Earth itself is providing the longest side of our Pythagorean equation. Part 4. Spherical geometry and world maps. Now, we need to see how this geometric rule actually governs the entire surface of our planet using a rotational coordinate system. We're essentially going to build a completely new world map based on this geometry. So let's systematically break down these new 3D world map rules. First up, that Seoul to antipode axis is our base, the diameter 2r. Second, imagine slicing the Earth exactly in half along that axis. The outer edge of that slice forms what we call a great circle. And this great circle acts kind of like a new tilted equator. Third, and remember Thales' theorem for this, if you pick literally any point P anywhere on that great circle and connect it back to Seoul and its antipode, you physically form a right-angled triangle inside the Earth. And finally, because it's a right triangle, our magical Pythagorean area rules still applies. Let's move on and see how this builds. Look at the equations we have here. Because point P can be anywhere on the great circle, we can use angles to describe its position. Using basic trigonometry, just sine and cosine, we define the lengths of our two shorter triangle sides. And here is the absolutely brilliant part. Because sine squared plus cosine squared always equals exactly 1, the total sum of the areas of those two circles we calculated earlier remains perfectly constant. It doesn't matter what angle you pick anywhere on the globe. Now, what's really interesting here is how this visually proves that relationship. Imagine point P moving along the Earth's surface. As it moves, one side of our internal right triangle gets longer, while the other gets shorter. Consequently, slice 1, which is one circle's area, shrinks, while slice 2, the other circle's area, grows. But mathematically, they are totally dancing together. Their combined area never, ever changes from 100%. And that brings us to the grand conclusion, the resolution of our core mystery. If you take the two smaller sides of that triangle connecting Seoul to anywhere on that great circle, and you use those exact distances to draw two flat circles, the total combined area of those two circles precisely, mathematically equals the area of the Earth's great circle itself, pi times the Earth's radius squared. The area of the Earth's cross-section is literally hiding inside every single right triangle you can draw across it. How wild is that? It is genuinely staggering when you finally zoom out and see it. So I want to leave you with this drop the mic thought. Next time you look at a globe, will you just see the physical land masses and geographic borders? Or will you see the invisible, perfect mathematical architecture, a 2,500-year-old law of area conservation, silently holding the dimensions of our entire planet together? Thanks so much for exploring with us, and keep seeking out those hidden structures in the world around you.